Okay, so let's now talk about the onboard DAC in the STM32 Discovery Board system. So, as you can see, we've been talking about just the general digital to analog converters having, 3, 4, 5 bits as we've looked at those previous set of slides. But for ours, we basically have a digital analog converter that can be used in either the 8-bit mode or the 12-bit mode. It can be used in conjunction with the direct memory access controller, but we're not really going to use that aspect because we will never talk about the DMA. In 12-bit mode, this could be left or right aligned. And what I mean by that is, typically we think of bits being 0 to 15 for our 16-bit numbers there. And so where did those 12 bits go? Could they go in the first 12? Could they go in the last 12? And so, we have to talk about that. It says we have 2 output channels for our digital analog converter. There's a specialty thing that I may need to point out there about something that your book shows, but each has its own converter. In this dual mode, conversions can be done independently or simultaneously when both channels are grouped together for synchronous update operations. So that, if you had 2 things that you wanted to be synchronized, you could have it doing the conversions like triggered together. It says an input reference pin VREF Plus shared with other analog peripherals is available for better resolution. An internal reference can also be set on the same input. Refer to voltage reference in this section. So this is the section in the STM32 Discovery Board or the STM32 manual. And so it says here a couple other things. The DAC out X pin, so there's the X could be 1 or 2, can be used as general input-output when the DAC output is disconnected from the output pad and connected to on-chip peripheral. The DAC output buffer can be optionally enabled to allow a high drive output current. An individual calibration can be applied on each DAC channel output. The DAC output channels support a low power mode, the sample and hold mode. Anyways, that's just a little bit more than we really will have to worry about. But one thing that we should point out is it said the output is disconnected from the output and connected to on-chip peripheral. So that's something that I may need to point out to you a little bit later. Again, here's some of the main features. We can do left or right data alignment in 12-bit mode, also 8-bit mode, and that's a little bit strange in how it can be done. It has this synchronized update capability. We can do noise wave and triangle wave generation with it. Let's see, what else did I want to... Oh, we can use external triggers, just like you could use an external trigger for the analog to digital converter. You can do that here as well. Each DAC output can be disconnected from the output pin. It can be connected to on-chip peripherals. And here is the following block diagram for our converter. So here you can see the converters. There you can see, the different ways. It talks about the timers that you could use to trigger. Also the direct memory access controller. So all that sort of similar. You have the output register, so as you can imagine, that's what you send out to the DAC to then convert to an actual value. Here's the sample and hold register, so these are things that you can set. Obviously you see the reference voltage sort of showing the pin that you can have there for both DAC 1 and DAC 2. You can see the LSI clock is tied to the two DACs. They are tied also to, all this you can see is tied to the APB1 bus. Let's see, here's the analog signal ground. You can see that there. We can do the offset calibration if we want to with those bits. So anyways, those are important aspects that you should see, and you can see that for us the input-output connections are for the one output channel is on port PA4, and the other output channel, DAC out 2, is on GPIO port A5. So they're right back to back. And notice that you can see here where they both have these op-amp buffers that are there, and you can go through the buffer or you can go around the buffer depending on whether or not it's connected or not. So that's an important thing here. You can sort of bypass that buffer if necessary. Okay. So now, as we start looking at every of the important aspects of this, is how are we going to talk about outputting something on the digital to analog converter, and what are the bit combinations that we need to set to enable it, what do we need to do to put things where, and so forth. So it says a couple of important things here. One, we can enable each DAC channel by setting its enable bit. So we have EN1 and EN2 for the first and second digital to analog converter channels. We see that there is this DAC CR, so the control register for the digital to analog converter is important, sort of like the sequence register and all that sort of stuff was for the A to D. So anyways, we have those. It says the ENX bit enables the analog DAC channel X only. The DAC channel X digital interface is enabled even if the enable bit is reset. So the enable bit is basically to enable the analog, digital to analog conversion. Okay. Now here's an important part that is worth looking at. It says, okay, what's the data format of the digital to analog converter? And that's important because you need to know how to put your digital value in that you're wanting it to output. And it shows here 3 possibilities for this single DAC channel. We have 8-bit right alignment. So here, notice we're showing actually the full 32-bit register here, but when we do just the 8-bit right alignment, we're going to put it here in those first 8 bits that we would expect. If we're going to do, and notice that it says the software has to load data into the DAC DHR 8RX 7 through 0 bit. So again, this would be 1 or 2 for that X, depending on which one you're doing. But notice, notice that we could just use like the DHR 1 or 2 just in the first place. So in any case, be aware of that. We have the 12-bit left alignment, so that's showing this particular case. So these 4 bits right here are nothing. So 0, 1, 2, and 3 don't hold anything for that. And so it's showing that, okay, we're going to put that DHR 12LX. So L is talking about the lower 16 bits, and then it's saying we're putting in the bits in 4 through 15. And then 12-bit write alignment says the software has to load data into this spot, and it's stored into DHRX as well. So the write alignment is going to have the standard way we would think of for the 12-bit number. Okay. Here it talks about dual channels, and you can see what happens. The big difference is if you're doing 8-bit, you can store everything in terms of just a 16-bit segment of the register, whereas for the 12 bits, you can either store it in the higher 12 bits of each 16-bit segment, or the more standard for what we would think, the lower 12 bits, the write-align version. And so that's all that's really talked about in these three things right there. It's similar to the other case. And notice, you can just have different values for the data holding registers that you're doing. It says, depending on the loaded DAC data holding register YYYD, the data written by the user is shifted and stored into the data holding register 1 and 2, which are internal non-memory mapped registers. DHR1 and DHR2 register then load into the DAC data output register 1 and data output register 2 registers respectively, either automatic by software trigger or by an external trigger event. And remember, if you go back and look at our diagram, that's where this is right here, right? These are those data output registers for the DAC, and you see it's tied directly into the converter. So the holding registers are what holds the data, and then it gets sent out. And we'll talk about that as well. Here it says the DAC channel is then enabled after a wake-up starting time. So this is sort of something that, again, we have to wait for after this wake-up. Maybe I should be careful and rephrase what I said. We can enable the DAC, but then we have to wait a certain wake-up time before it actually is enabled. That's probably the better way to put it. Okay, so this is basically saying, where do you put the data? You have two choices. I think you can see in general, if it were me, and you have the choice here, I'm not going to make you do something. You have to be aware if you get on some project and somebody else has done something, but in general, I would think that most of the time we would do something right-aligned. It may be done the other way if there's some old system that was storing something in a different format. But for us, I think it's easier to do it as right-aligned. And so if it's 8-bit, there you see that. If it's 12-bit, there you see that. And the data holding registers will tell you how that data is stored. Okay, so what about the output register? It says here you can load both at once using, it says the dual DAC 8-bit write-align data holding register. So this is one of them, and this is the other one. So that's the two DACs data holding register. You put the data there, and if you want to do it for 12-bit conversion, you'll do it there. And again, we already pointed out, it doesn't really matter which way you do it, but 12 bits in each will require the data holding register to use all of the 32 bits. One of the things that I think is sort of confusing about it here is that, you can call things by different variables. This DAC DHR8 HD RD and DAC DHR12 RD. So they're both sort of similar, and you can imagine that you can get something from each one of them, but in any case, it's just something that you need to sort of remember in terms of what kind of data you're going to be doing and outputting. Okay, so again, how do we use it? Well, if we have our digital to analog converters, you know, we have these two right here that we're trying to put PA4 and PA5. And okay, so we have to set, just like the analog to digital converter, we have to set the pins for PA4 and PA5 to analog. So here you see it. We have to put the motor register, and now notice, you know, remember that analog mode is 1-1, and so that's the 3, and this is moving it over, doing a left shift 4 times for PA4, and it's 2 bits per you know, for the motor set up, for the setup there, these 2 bits right here. So this is basically saying we're moving 1-1 into PA4, and then we're moving in this one 1-1 into PA5. So that's all this is doing, again using the motor register just like we've seen so far before. Excuse me. We have to turn on the clock for the digital to analog converter, and you can see that right here. We're doing the sort of DAC1 enable. So again, this is a specific bit pattern that you'll look up in the startup file and see, and you can imagine that, you know, you have to do this, and then you have to wait up that T wake up start time. Notice one difference is the bus that we have here. Again, a lot of these naming conventions seem crazy, but you have to remember they're defined in the startup file. And again, we're just exclusive ORing, not exclusive ORing, we're bitwise ORing the different bits so that we can enable the DAC here. Then we have to turn on the channels. So what's going on here? Well, we take the DAC control register. In both cases, here we see that we're moving 0 times just the number 1. Well, 1 is 0, 1, right? So we're putting a 1 in that bit 0. What is that doing? It's putting a 1 in bit 0 right here. So we're putting 1 in this enable 1 line. And then, what's this one? We're putting in 1 and we're moving it 16 times. We're still doing DAC 1, right? So we're still doing DAC 1. We offset it 16 times, so it goes all the way up there and then to here. So we're putting in a 1 there for this one, so this enables channel 2. So we've enabled channel 1 and channel 2 for DAC 1. Okay, so you know, this is the example code that we just showed before for enabling the DAC. Here we turned on channel 2. That's the second one we did there. Now, what are we going to do if we're trying to do some output for the data into the digital to analog conversion? This is basically trying to say something to you right here. Okay, let's say we had an analog to digital value that we used the A to D converter, and it gave us a 12-bit value. Well, what's it saying? here it's saying, oh, here was the A to D value that we read in. So this is the value we read in from the data register from the analog to digital converter, what we discussed in the previous lab lecture. And we're going to then put it into the 12-bit to put it back out, the output of the digital to analog converter. So basically this is telling us, okay, we're taking ADC, so we're reading in analog from ADC, and then we're outputting it back out to the DAC. That's all this is doing. So this is basically saying whatever you had in that data register from the analog to digital converter, you're putting it back out on the digital to analog converter. Okay, so what about this next lab that is going to do a little bit of the analog to digital conversion and the digital to analog converter? What we're basically doing is using that same part that we did from lab 3. Now what we're going to do is we're going to do a couple of things. Okay, it says, what are we going to do? Well, we're going to set pin A5 to analog so that we can use, again, oops, went past it, DAC 1 out 2. So we're going to use the first DAC out 2 on PA5, and we're going to take readings from that analog to digital converter on pin 2, so that's like what we did last time, and copy this data to the DAC. So we're going to basically read something in on the analog to digital converter, and then we're going to write it back out on the digital to analog converter. And it says, using a signal generator and oscilloscope, what is the max frequency that can be transferred? And it says, don't display anything on the LCD. So you don't have to worry about the LCD this time, but what you're trying to do is see, okay, if I hook this up and I have a sinusoid coming in, what is my actual, how fast of a sinusoid can I read in and then put it back out and it still looks right? So make sure when you set this up, I'm sure Jitendra will be there and can help you, but don't decide that you're going to use something like, 20 megahertz to start out as your frequency. Do something low, super slow, 10 hertz, 15 hertz, 20 hertz, just to make sure you're doing things right. That's one of the things that I think you have to start grasping with, is now that you're getting into circuits lab and you're starting to do things more on your own, and you'll see this in electronics lab for sure, you have to make decisions about how you're going to test something. And always try to, they talk about the KISS method. I don't know if y'all have ever heard this before, but it's called keep it simple, stupid. But it's really great. Don't try to do anything advanced first. Try to dumb it down as much as you possibly can, and then that gives you confidence that if it does that, you can move forward and make something a little bit complicated. So don't try to run this with a real high frequency at first, because maybe you've picked a frequency that would be too high. Pick a really low frequency and see how fast it can track it. That's basically what you're seeing, is how fast can the analog to digital converter convert the frequency into the digital data points that you want, and then that DAC output, how can it translate it back to give you that sinusoid. So obviously it's not going to be perfect, because you're going to have a digitized version, maybe I shouldn't say digitized, but a discrete version of the analog output that's much more like that kind of setup. Okay. And then the next part of the code is basically going to just be modifying the output. You're going to put in a sinusoid, and you're going to see an example of it here. But if the input is between 1 volts and 3 volts, so let's say you have a sinusoid that's like 3 sine of omega t or something. Well, when that's between 1 and 3, you're going to change the output to be 3.3 minus Vn. Now, make sure you remember that, okay, you're reading something in, and you have to realize what's going on with these numbers, the digital converter, how does that relate to a specific voltage value, and so forth. So you're going to have to look at that a little bit and play around and make sure you understand what's going on there. And then if the value for the voltage is greater than 3 volts, then output 0 volts. If it's less than 1 volt, then put out 1 volt. So you have this, and obviously, you can put a sinusoid in and test all of this, or a ramp, or something like that. Or you can be specific and say, I'm going to put in just 1 volt. You could put in a DC voltage source of just 1 volt and see what happens. You should know if you, or maybe I shouldn't say 1 volt, but let's say I put in 2 volts. So you should know that if you put in 2 volts, it should run this segment of code and output this and give you 3.3 minus 2 out, and so forth. So make sure you realize that you're basically doing sort of a if-then-else statement to try to get it to manipulate the data that you're reading in and output something that you want based on that data. So here is the main setup. We have to set up that port that we already talked about for analog mode. We have to enable the clocks. We have to turn on the analog to digital channel 2. We have to look at the control register. This talks a little bit about connecting the function generator to the PA2 pin. So that's the analog to digital converter part. And then connecting the oscilloscope. So this is what you're going to view the output on from the digital to analog converter as it shoots it back out, and observe the oscilloscope with that. And then increase the frequency. And it says, make sure when you do this for the second part, remember to use the digital values for 3 volts and 1 volt. So you have to know from your knowledge of how that digital analog converter works with the resolution that it has and the reference voltage, what is 3 volts, what is the digital representation in 12 bits for 3 volts, and what is it for 1 volt. You have to know that if you're going to want to go ahead and manipulate that. Here is sort of an example of what happens when you're looking at it. So you can see this is sort of the output voltage, and it corresponds to what's supposed to happen with the input voltage. It's supposed to do something for the different ranges of above 1 volt, below, in here he should have also maybe put what the actual input voltage looks like, but this is what the output voltage looks like as you have translated it yourself by bringing in the data, doing the if-then-else stuff, then sending it back out after it's manipulated. And then next week we'll be doing the Etch-a-Sketch. And so if you look at this, you'll see the next lab has something similar to this particular lab. Again, obviously you're doing this digital to analog conversion, and you can see that the way that is on the oscilloscope, you're getting it to plot something on the oscilloscope based on whatever the input is. This has given us a particular subroutine or function call called vconvert, and it says, okay, this converts something from a voltage to a 12-bit number, and it says fill out this draw line. So this is a subroutine for you that you will need to write, so you can draw something that will draw a line from point x1 y1 to x2 y2, and it's just going to draw that if you do it. And you'll have to use the oscilloscope in the XY mode. Now, what is the XY mode of the oscilloscope? That is basically, most of the time in circuits you will have something going as a function of time, and you'll have this input voltage. But if you put two voltages on there and then you do one versus the other, it's going to be the XY mode. So channel 1 can be your X channel, channel 2 can be your Y channel. And you haven't done this particularly too much, because I don't even know that you will have gotten to the oscilloscope lab so far, but basically, you're going to be doing maybe I should say V1 and V2. So that's the graph that you're going to be doing, and you're just basically trying to make a little etch-a-sketch or draw something out on there. So that's what it's showing you here, and you'll see an example. This is something that you can output on channel 1. This is something you can output on channel 2. So this is looking like a something that's crazy looking as a function of time, but here's what it looks like when you graph it in XY mode. So it's just you can see these are just vertical lines and horizontal lines, so all that we know about, and then that's drawing a circle. So you have some information about how to draw the circle. And again, this is something you're supposed to play with and learn something about. So this is not this week's lab at all. This is the lab for next week, but I thought I would go ahead and talk about both of them, because you actually will have the knowledge to do both of them after we finish this lab lecture, which we have just done. So it might not seem like you really get it, but you'll have to look at that template for V-convert, and hopefully you can have a chance to do that maybe this week after you finish the lab. Look at it, see if you can't generate some ideas about it, and then start looking at how you would modify that to do the drawing the line and so forth. And it doesn't really matter what you do. I believe the previous TA drew I can't think of it, the Illuminati symbol. So he had like the triangle with the eye, or whatever you want to say. So there's a number of things that you could do, but just do something that is unique and shows that you know how to go through the process of doing that and understanding the the analog to digital converter. The digital to analog converter. Okay, sounds good, and I will talk to you all in the next lab period.